Okay, class, we are starting another example, section H.2, areas and lengths and polar coordinates. That's the section we've been looking at. And let me give you a moment to copy this example down. Okay, so this problem, now here, we want to find the area of the region that lies inside the circle, r equals 3 sine theta, and outside the cardioid, r equals 1 plus sine of theta. So what we have to do is we're going to go to Desmos and we're going to graph both of these. Okay, so I'm going to Desmos and you're going to Desmos. Okay, and generally I like my angle to go from 0 to 2 pi on my graph. Let me just hold on here. Hold on here. Okay, we'll go to Desmos. Okay, and maybe we can zoom this up a little bit. All right, there's a picture. There's a picture. So you have a red and a green graph. The red graph is the circle r equals 3 sine theta, and the green graph is the cardioid r equals 1 plus sine of theta. And what we want is we want the area of the region that lies inside that circle, that red circle, and outside the green cardioid. Okay, so area inside the red circle, but also outside the cardioid. Okay, so if we go back here, go back to the problem at hand. No, that's not it. Hold on. This is the one. This is what we're looking at. So the cardioid and the circle intersect each other. And based on the shading, that gray shading in the picture, that's the shading where of the region that lies inside the circle and outside the cardioid. The region itself has this starting angle and this ending angle. The starting angle is theta equals pi over 6. The ending angle is theta equals 5 pi over 6. Now, I'll tell you, I'll tell you how I get that, and then I'm going to stop for a minute so you can copy. You set the two equations equal to each other, okay, and the sine of theta equals a half. Well, that's going to be true for when theta equals, pi over 6 and 5 pi over 6. In other words, the sine of (30° is equal to a half, and the sine of 150 degrees is equal to a half. Okay, because they both have, you're in the, well, yeah. Okay, so that's trigonometry. That's trigonometry. So that's how we get then this starting angle where the shaded region begins, and then this ending angle where the region ends. So let me give you a moment to copy here up to here, and please let me know if you have any questions. Okay, so in this problem, the area of that blue shaded region is like, well, if we were to look at this integral here, well, no, let me do this. Sorry. Yeah. So if I'm tracing out in purple that purple region, and that purple region is this purple region. And the area of that purple region is given by 1/2 3 sine of theta squared, where your limits go from pi/6 to 5 pi/6. That's that region. Now, if we trace out this other region, and I'll try to do it, the best I can here. See there, I'm tracing out in green. If I trace out that region, notice the border, the polar function on that region is r equals 1 plus sine theta. So this region here has this integral, and the limits go from pi/6 to 5 pi/6. If you, hey everybody, teach, if you subtract this region from this region, you're going to get the shaded region. You're going to get the shaded region in the picture above. You're going to get that blue shaded region that you see. Right? Are there any questions on that? Any questions? All right, now it's a computational problem. Now it's a computational problem. So, all right, let's think here what we have to do. We have two integrals that we need to work out. Now, of course, I think it goes without saying that here that we're going to need to FOIL this. 1 plus sine of the quantity 1 plus sine theta squared is 1 plus sine of theta times 1 plus the sine of theta. So it goes without saying we have to FOIL that out. And when we do so, we're going to get what you see up here. The second integral is the integral of a sum. So I'm going to write that as the sum of the three integrals. You do these problems step by step. With these kind of problems in section H.2, you want to be very careful when you work them out because you don't want to make unnecessarily a mistake. And that means I show a lot of steps. This example that we're doing is actually example 2 in the textbook, and I'm putting in a lot more steps than they do. Okay, because sometimes textbooks, it's a great textbook, but all textbooks sometimes, to save space, they leave out a few steps. They give enough so you can figure it out, but I'm trying to give you a lot of steps here. So, are there any questions up to here? All right, well, notice here that you have hold on here, you have a 9/2 times the integral of sine squared. And then you have a sine squared integral here. And of course, that's being multiplied by negative a half, and it's being subtracted. So if you have, like, 9 halves minus 1 half, that's 8 halves, which is 4. And this is how we get that first integral down here. Baby steps, baby steps. That's how I get that integral there. Okay, so I combine two like terms, two like integrals. And then I write out the other two integrals. And that gets me to there. Please let me know if you have any questions. Okay, now we could get the antiderivatives for the sine squared, and we would need a trig identity. That we'd have to write sine squared as a trig identity first. But we could evaluate these integrals with the limits 5 pi over 6 and pi over 6, and that's okay. But 5 pi over 6 is, that's 150 degrees. That's a little bit more difficult angle than maybe we need to use. In other words, I like angles. I mean, that's fine. We could do it that way. We could evaluate those integrals with those limits. But angles like 0, pi over 2, pi, 3 pi over 2, 2 pi, those are really nice angles. So if I can rewrite for these integrals, in a certain way, it could be helpful. So what I'm going to do is I'm going to look at the graphs. Actually, I'm not going to worry about the one. This integral here, the middle one's easy to do. But I'm going to look at the graphs of the sine of theta and the sine squared of theta. Okay, so on the next page, I've drawn the graph of the sine squared of theta. Notice I draw it from pi over 6 to 5 pi over 6. So this is no different. Like in Desmos, you could say, hey, graph sine squared of theta from pi over 6 to 5 pi over 6, and you'll get a graph. And the pi over 6 is 30 degrees. 5 pi over 6 is 150 degrees. 90 degrees, which is pi over 2, is right between those two angles. And the sine squared of theta, okay, is the based on the graph, the areas. Hold on here. Did it not? Hold on. Yeah, the areas are the same to the left and the right of pi over 2. So we can use symmetry of the sine squared of theta about pi over 2 to help us. The sine of theta also is symmetric about pi over 2. This allows us to, we're focused here on the first integral and the last integral. right? I can rewrite the first integral as 2 times the integral from pi over 6 to pi over 2. See that? I can do that by virtue of the fact that the areas are the same, about pi over 2, based on the picture there, the left and right areas. I can similarly do the same thing for that third integral. The integral of the sine of theta from pi over 6 to 5 pi over 6 is 2 times the integral from pi over 6 to pi over 2. So you see, I was able to get in. Let me just, I don't want email interfering with our lesson here. So let's make sure everybody's comfortable up to here. Now again, you don't have to use these tricks, okay? Or they're good. I want to say this the right way. They're not really tricks, but you know what? They're just ways to help make integration easier. Okay, so I guess you could call them tricks, but they're mathematical. They're based on math, based on the symmetry of the sine squared and the sine of theta about the angle pi over 2. I can rewrite 2 of those 3 integrals for my area as much easier integrals to work with. Mark, there will not be an issue if the limits are not changed. If you wanted to go with pi over 6 and 5 pi over 6, then that is fine. I'm just doing this because the book, like an example 2 does it, and I want you to know what's going on there. Okay, I want you to know what's going on. Okay, and let me just see here while I'm at it. Mark, if I may, am I correct that you're going to be doing a presentation on Friday, December the 10th at 9 a.m. on redesigning the National Institutes of Science and Technology? For the MS NIST colloquium? Am I correct on that, Mark? Okay, so I'm giving kind of a shout out there. Mark, I'm sure would be happy to share the link to get to, if you wanted to, maybe even on Wednesday, if you wanted to see him this Friday, do his presentation. Congratulations, Mark, on that. All right. Okay, let's continue with the computation here. Let's continue. So we go to the next page. Okay, and hold on now. Let me see where I'm at here. One moment. I'm wondering if I got my pages. Now, this is what I want. Yep, this is right. So now I get my antiderivatives and I do my computation with those antiderivatives. So it's really just a matter of being careful. We only have one more page here, class, after this, so I'd like to finish this example so we have a complete example done. So we might go a few minutes over, but it won't be long. It'll be on the recording if any of you have to go, to leave a little early, well, leave, you know. But if you can stay a little bit, I appreciate it. I mean, this is just calculus, integration. It's all you're doing here, nothing fancy. But there's a lot of expressions, so you have to really make use of parentheses and grouping symbols to keep everything straight. Are there any questions at all here before I go to the next page? And we'll finish this example. Okay, so now it just comes down to evaluating some, like the sine of pi over 3, the sine of pi, the cosine of pi over 6. You just evaluate those and work it out, and in the end, that area is going to equal pi. That's the area of that shaded region. That lies outside the circle, r equals 3 sine theta. I'm sorry, that's the area of the region that lies inside the circle, r equals 3 sine theta. And outside the cardioid, r equals 1 plus sine theta. You can be sure you're going to have problems like this on the final exam. And this is very important too for multivariable calculus. If you have to take Math 280, for instance, it'll help you there as well. All right, are there any questions before I stop the recording? Who thinks this is who thinks this is interesting? Who feels this is interesting, these polar coordinates and what you can do with them? All right, Clea likes it. Okay, and who else? Mark likes it. Good. And there's a third person. Forgive me, third person, if oh, Victoria likes it too. Okay, wonderful. Avery does too. Great, great. All right. Let me stop the recording if you're good here. Excellent.